I would like to describe a field in which little has been done, but in which an enormous amount can be done. This field is not quite the same as the others in that it will tell us little of fundamental physics, but it will tell us much about the strange phenomena that occur just below our perception. In contrast to the natural philosophers of the past, the scientists of this field delve into the recesses of nature and show how she works in her hiding places. Their quest is to understand and create the imperceptible. After all, there is plenty of room at the bottom.
Hey everybody, welcome to the Materialism podcast, an exploration of the past, present, and future of material science and engineering. I'm your co-host, Andrew Falkowski, and I'm not joined by Dr. Taylor Sparks. Instead, I'm joined by our editor, Jared Duffy. Jared, how are you?
I'm doing good, Andrew. How are you?
Doing all right. I slept a lot better last night than I did a couple of the previous nights.
Oh, yeah.
So I'm feeling better, eating a little bit better. The semester's over, so we're in the summer period. So things are a little calmer, maybe a little bit too calm.
See, not for me, actually. I foolishly am actually taking more classes over the summer than I took in the spring.
Why?
I don't know. I haven't really thought of a good reason for it. I just like saw classes and I was like, oh, I want to take that one, I take that one, I take that one. And they were only offered in the summer, I guess. And so they just kind of piled up. And now I'm taking I think I'm taking 4 more credits than I took in the spring, but that's okay.
How many total?
I'm only taking 8, Between balancing the full-time job with the school, it's required some delicate skills. So,
well, it seems like you're interested in them. It sounds like you're taking them for the right reasons.
Oh, yeah, definitely.
Well, we're starting to leave springtime. It's warming up, which means we're entering the time of hot seatbelts, air conditioning, high electric bills.
Seat coolers. Never forget seat coolers.
My car doesn't have that.
Oh, wow. Some of us are a little cooler. Yeah, it does. It kind of makes you feel like you're like really sweaty almost for a second. Though. It's like a weird sensation, like the cooling seat. I don't know. Like,
well, I guess when you're sweaty, you
too.
Feel like you're cooling off. Like that's the mechanism that's happening. And so if your skin is being cooled, I guess that would feel.
Yeah.
I have some stupid setting in my car where if it thinks it's too hot or too cold, it goes into this auto AC mode until it satisfies its constraints. And I turned it off at one point, but then there was some engine troubles and whatever. The dealer reset my car to the factory settings, and now it's on again. I do not know how to disable this auto feature because it'll be like I'll be hot or I'll be cold, and it's like nope, I'm doing my own thing for 20 minutes.
Just start pulling fuses until something works, maybe.
But overall, cooling's a challenge, especially in more arid and hot climates. And while we have technologies for cooling, these put pretty high demands on our grid system.
Oh, yeah, definitely. There's actually something very prevalent to me, which was growing up in California. Anytime there was a heat wave, we had these great rolling blackouts, which was really fun. And I know Texas and a few other states that have heat waves tend to suffer from that issue where the grid just can't sustain that much AC being run.
Mm-hmm.
And then I think even in Europe, there's like actual hard numbers. We saw in Italy and Spain that they can't cool lower than 80 degrees Fahrenheit because they want to reduce like energy consumption. So
part of that was trying to reduce the reliance on
Russian
energy
gas,
from Russia. But there was certainly another component of trying to reduce energy consumption overall. And while air conditioner efficiencies are improving, with these technological improvements, we're also seeing higher complexity, meaning that these are harder to repair, higher upfront costs, and I think the gains are starting to get pretty marginal in terms of what you're getting.
Something can only get so good, I feel like. At some point, without inventing like a whole new mechanism for cooling, it just kind of becomes smaller and smaller gains.
This is where cooling paints or coatings come in. These provide a potential low-tech solution for cooling buildings and structures. Many of these are already painted, which means this is an attractive fit. Right? If you're already going to have to repaint your building, what if you could paint it with something that can cool it without any moving parts or repairability needs? We're not just talking about simple white paints either. Those typically use titanium oxide as a pigment. Same pigment that makes Oreos white too.
Yeah, actually, if you remember from our titanium episode, we actually discussed titanium oxide and its uses in food and other things.
And when I think about titanium oxide, I think about ceramics. And when I think about ceramics, I think about the American Ceramic Society, who sponsored this episode. And if you stick around closer to the end, you'll hear how you can get access to over 100 years of ceramics content for free. So stay tuned. So maybe to dive in, before we get into the materials aspects of how these paints work, we should get into the physics that these paints are exploiting to actually provide cooling. These work by passive radiative cooling, which occurs by simultaneously reducing the amount of solar radiation that's absorbed by these paints and maximizing the amount of energy that is emitted as thermal radiation.
So let's talk about reflection first then.
Right, and it's not just reflection, it's also scattering if we want to reduce our absorption, and we want to do this specifically within the solar spectrum. And this spans wavelengths from approximately 250 to about 2,500 nanometers. So we get a little bit of the UV range, all of the visible, and the near infrared range. And for reflection and scatter to occur, we can start by looking at the refractive index mismatch between mediums. So between air, which has a refractive index of 1, as light propagates through air and then wants to go into a new material, if that has a really high refractive index relative to air, you have a higher chance for reflection or scattering to occur, just due to the need for conservation of energy. This can occur between the air and the pigment in the paint, but it can also occur between paint components as well. So you could have between the pigment and the binder, for example. So there's a lot of opportunity for reflection and scattering events.
And this is similar to impedance matching, which we actually talked about in the last Andrew and Jared special, radar absorbing materials.
Was that the last one? It's been a while since Jared and I have been behind the mics. Looking at scattering more specifically, scattering is a way that we can direct light away from the material and enhance the potential for reflection events. And it's typically divided into two types when we're referring to cooling paints. We have Mie scattering, spelled M-I-E, thought it was Mie. This occurs when the size of our particles, like their diameters, are greater than or about equal to the wavelength of light. This is the dominant mechanism within the solar spectrum, especially for cooling paints. And within this, smaller particles tend to scatter shorter wavelengths, like UV, more effectively, while larger particles tend to be more efficient at scattering longer wavelengths.
So it sounds like we want a broad spectrum of sizes then.
Yep, that's right. The most successful strategies have a pretty wide spectrum, which is sometimes counter to what we go for when we're talking about particle sizes. In a lot of applications, it's all about making that as uniform as possible, but here that's not the case. On the other hand, you also have Rayleigh scattering, and this occurs when particles are much smaller than the wavelength of light. And in the case of cooling paints, you could have an instance where you have a bunch of fine nanoparticles in the paint that might contribute, but the overall contribution is generally less significant compared to Mie scattering. The last important physical concept is the band gap of a material. This is the energy separation between the valence and the conduction band of a material. And if photon energy exceeds your material band gap, then that energy is going to be likely absorbed. However, if your band gap is greater than the photon energy that's incident, then the material will be transparent to that light. But that doesn't necessarily imply reflection either.
You know, speaking of reflection, this reminded me of something about how careful you need to be with reflection. There was a story a while ago, and I think this was 2013 in London. They had just added these new floors to this building called the Walkie-Talkie skyscraper. Interesting name, I'm not sure why. And what happened was the way they had curved the glass on these new floors, when it reflected, it created essentially like a focused sunbeam. The way I saw it described, which I really liked, was similar to a magnifying glass to ants. And basically this beam started melting things, and it scorched shop fronts. It melted a car, actually. I think the hottest temperature they recorded on it was like 240 degrees Fahrenheit, which is like 116 or 17 for our European friends. But the craziest thing, like story that was a little publicity stunt, was someone went there and they cooked an egg on the pavement to prove it was possible. They ended up just putting like sunshades and just doing their best to change how the sun hit it. But then, funnily enough, the architect built another building in Las Vegas, and the same thing happened there.
Architects are wild and out there, trying to create all these complicated geometries to look cool, but that's pretty bad.
The best thing was he blamed part of it on global warming. He just said he didn't realize it was going to get so hot.
Yeah, he created a concave dish.
Yeah, I know. But again, he's only an architect, okay?
Well, and it's not just about reflection. We also want to increase the emission of thermal radiation from our material. And emission in this case takes the form of energy typically in the infrared or the visible range. And we typically measure it in terms of emissivity, which is a measure of effectiveness relative to a black body at a similar temperature, which is going to be your perfect emitter. And through this emissivity, this is the mechanism that allows these paints to actually achieve a cooling effect, because not only are we reducing the energy that we absorb by maximizing our reflection and scattering, but here we're actually pushing energy away from our structure. And it's not just any emissivity, any wavelength. It turns out we actually want to be very selective of the wavelengths that we're emitting.
Yeah, wouldn't the heat just get reflected back because of the greenhouse effect?
Yeah, that's right. Under very specific wavelength ranges, water and CO2 will absorb thermal radiation and just re-emit it. And this is what causes the greenhouse effect, as you mentioned, and temperatures to rise. But it turns out as we go towards the 8 micron to 13 micron wavelength range, so this is long wave infrared region of the spectrum, there's a window where there aren't any gases in the atmosphere that will absorb and re-emit this. It's called the atmospheric window. And if you can direct thermal radiation in that wavelength range, it'll escape to outer space and effectively cool the Earth. It's not going to get reflected back. And so this is typically what we want to selectively try to emit within. And emission is in part governed by intrinsic material properties of the paint components, specifically their ability to form what are known as phonon polaritons at the right frequency. So in materials like silicon oxide, the metal and oxygen bonds create electric dipoles that oscillate when they're stimulated by infrared radiation at very specific frequencies. And this interaction creates a photon-phonon coupled state, where electromagnetic energy temporarily converts to mechanical vibration energy. In other words, they're resonating at natural vibration frequencies of the crystal lattice. Other oxide ceramics like alumina or calcium carbonate and some polymers with polar bonds also exhibit these resonances, and these are typically what are going to be included within these paint materials. It is worth mentioning that the sky temperature is usually below ambient temperature, and so broadband emitters can still have a cooling effect, but this ends up getting mitigated because it's often reflected back. These will primarily provide that selective emittance that we're looking for, although broadband emittance can still be effective, although the net effect ends up getting mitigated by greenhouse gas reflection, but still the sky itself is typically a cooler temperature than ambient, and so it can be effective for cooling.
Just not as effective as if you
Not
take
as
the
effective.
specific wavelength. Okay.
Yep. So that's the physics of how these are working. Maybe we can get into some of the materials. Jared, what are just some like broad categories of things that we need to make a paint?
Well, for paint, we need pigments, binders, solvents, and additives.
That's right. The pigments provide color, and they're also a bulk of the mass.
Yeah.
Binders are going to hold those together. They're going to give them nice mechanical properties and act like a glue. Solvents are how we dissolve it and make it nice and liquid. They're what eventually dissolve and leave the paint behind. And additives can impose all sorts of different properties. The pigments are doing bulk of the work here, so maybe we can talk about those first.
And the first one, which we touched on earlier, we'll talk about is titanium oxide, or titania.
Yeah, it has a really high refractive index, 2.5, 2.7, much higher than a lot of the other oxide ceramics, but its band gap is really low, like 3.2 electron volts, much lower than the UV photon energy of 4.96 electron volts, which means you're going to get absorption. And that's problematic for a couple reasons. It makes titanium oxide photocatalytically active, meaning you form reactive oxide species that can degrade your polymer binder, so you'll get chalking and yellowing. It makes it look ugly, and it's going to reduce the effectiveness of your paint. Though interestingly, you can mitigate this by using fluorescent pigments, and these absorb UV light and re-emit it as visible light, which can then be reflected and scattered.
So using this, does that mean if I take my Oreos outside that they'll be slightly cooler?
I don't think anybody has tried. I just had an incredible idea of how to win an Ig Nobel. If we took Oreos, open them up, put them on our roof with the cream side facing up, can we achieve higher cooling as a result of that?
Well, here's the question.
What's the cost of Oreos per square? It's got to be more than paint.
But what do you do with the leftover Oreos? Because you're going to have half an Oreo every single time left over. Yet no one wants an Oreo without the cream on it.
I'm going to be honest.
Yeah?
I kind of just like the cookie.
Oh, okay. Well, there we go.
I'm going to eat all of them.
Someone do this, and then they just send all the cookies to Andrew.
But here's the thing. Oreos could be expensive, but there's probably a lot of expired Oreos out there that they just throw out.
Yeah.
They're no less white, but they might have other problems.
So let's talk about another material maybe that won't have these problems.
That's right, silica or silicon oxide. Not nearly as high of a refractive index, 1.45, 1.46. And as a result, you need really high particle concentrations in order to compete with titanium oxide in terms of scattering. But it does have a really high band gap, around 8 electron volts, so we're not going to get any UV absorption. What's really nice, as I had mentioned earlier, is that silicon and oxygen have strong intrinsic phonon-polariton absorption bands in that mid-infrared, particularly around 9 microns of wavelength due to silicon and oxygen stretching. But in the bulk, it actually has this weird narrow reflection peak in that region in the form of what's called the Ristral band. But typically when you've broken this up and if your surfaces are textured in some way, it ends up not being particularly consequential. Going down our common oxide ceramics, we'll end up with aluminum oxide, a little bit better of a refractive index, 1.75, 1.77, great band gap, 7 to 9 electron volts. It has strong absorption bands in that mid-IR range, meaning that it also has great emissivity in that range as well. And it has great UV durability, often outperforming titanium oxide. A number of really low-cost paint solutions are using alumina, sometimes coupled with silica or a few other things. So it's a great material all around. Maybe something that wouldn't come to mind is the next one in our oxide sequence, but one that's risen to prominence is barium sulfate. Refractive index 1.64, 1.65. Good band gap, about 7.27, but it has exceptionally high solar reflectance with values reported in the 97 to 98% range. But you need really high particle concentrations, like 60 volume percent, because of that lower refractive index. But it's been making waves.
Yeah, actually, speaking of making waves, there's a really interesting article I was reading that Purdue made a paint using this, and they actually said that if they put it out in the sun, they were able to get it 8 degrees cooler than the ambient temperature, even under strong sunlight, and at night it was 19 degrees Fahrenheit cooler than ambient.
Which, if you're like me and you like to sleep cool, that's a win.
And they also use what we talked about earlier, having different particle sizes. And they had discussed they could make it even better if they had a slightly higher particle concentration. But they said the trade-off is the higher the concentration, the easier it's going to be for the paint to break or peel off. And at that point, it's less useful.
Yeah, I mean, at that point, the amount of binder you're going to have relative to your pigments, it's just going to be too weak. If you've ever made a ceramic slip and you dry it, there's a certain threshold. I mean, well, the other problem is at that loading, you might even just crack, the particles just might crash out of your solution. You're not even going to be able to contain them in a dissolved state. So that makes sense. The next one we'll see in some more low cost applications is calcium carbonate. Pretty comparable refractive index to barium sulfate, band gap of 5 electron volts. So we're kind of getting in potentially into the danger zone. Can be a little bit better. Also pretty weak intrinsic thermal emission in that atmospheric window that we're interested in. In fact, when it's used in paints, the emissivity is primarily from the polymer, and we'll get to how that works, but it's really low cost. High abundance, has good solar reflectance with good UV stability, and it's often actually used in combination with other more emissive materials like silica to get a better balance of solar reflectance and thermal emissivity.
When Andrew says low cost, he means it because, first of all, we can get it from eggshells, but also you may recognize it because it is the main ingredient in both chalk and Tums. So likely you've had a lot of experience with it in your life.
Yeah, in that sense, it's a bio-waste product and one that could be sourced pretty cheaply. Going through the literature, you'll find a lot of different oxide pigments that are used. You'll see magnesium oxide, zinc oxide, yttria. It seems like a lot of these work to varying degrees. I think one of the big pushes right now is how do you make this as economical as possible, because you're trying to compete with a paint industry that has scaled and existed for quite a long time, and you're not going to be able to take advantage of economy of scale to the same degree, or maybe market dominance and the ability to get the right materials and supplies compared to some of them. So bringing down the cost is really important. Some other interesting composite particles we'll see include silicon nitride and iron oxide, which are able to help broaden the emissivity across the atmospheric window, which is generally what we're looking for.
All right, so what about the binders then?
These serve a number of critical functions to the paint, hence why you're kind of limited on the maximum volume percent of pigment that you could add. First, they provide dispersion and adhesion, basically creating a much more uniform spread of our pigment within the paint film. And they provide adhesion to the coated surface, keeping that thing kind of glued down. They also provide some nice mechanical properties, not only strength, but also flexibility, which is really important. When things heat up, they expand, and so you want at least the ability to accommodate that a little bit. In addition to when paints are drying, they're also undergoing shrinkage and expansion. They can also provide some nice abrasion resistance to the dried paint film, which is good. There's also an important optical contribution. Aside from the pigment itself, the binder can also contribute to the emissivity, but it can also contribute to the absorption, which can be problematic. And it plays an important role in which polymer binder you actually end up choosing. So a really common one that's been used a lot throughout the literature are acrylics. These are things like polymethyl methacrylate, which you may be familiar with, good transparency, reasonable UV resistance, but it can yellow over time. So you often have to include UV stabilizers if that's the route you want to go and you're looking for longevity. You'll also see silicones, polydimethylsiloxane, PDMS, great UV stability, low solar absorption, which is good, great emissivity because of those SiO-Si bonds and their vibrations. And they also offer pretty good hydrophobicity right out of the bag, so you can get nice self-cleaning properties from those. You'll also see quite a bit of work on fluoropolymers. This is because they have the lowest absorption within the solar spectrum. They also have great chemical inertness, UV resistance, and durability. And especially compared to acrylic and silicone, they have far fewer carbon-hydrogen and oxygen-hydrogen bonds, which tend to absorb sunlight far more than carbon-fluoride bonds. And so you're going to absorb less UV than acrylic and further enhance the amount that you're reflecting. But one of the big problems is current concerns over forever chemicals from these fluoride polymers and their ability to eventually leach into the environment from these paints. Polyurethanes also come up. They have a couple of really good bonds for infrared emissivity, including the carbon-oxygen, nitrogen-hydrogen, carbon-hydrogen bonds, and have been shown to be pretty good results when paired with alumina. But regardless of which polymer binder you're using, an important part of increasing scattering and reflection is actually structuring that binder a little bit through the inclusion of pores within the polymer matrix. These are effectively creating air pockets, which are going to have a different refractive index, increasing the amount of potential scattering that can occur.
Yeah, that's right. And that's actually why snow appears white, because even though ice crystals themselves are transparent, when you stack them all together to create like a clump of snow, there's so many small gaps and pores in between each ice crystal that you actually create a white look.
Yeah, and this is also a effective means of cooling the earth. In fact, isn't that why this company, I forget what the name of it is, they want to bring back woolly mammoths to go pack down the tundra to keep a successful snowpack?
I did not hear that. Is that actually what they're thinking about doing?
Yeah, supposedly this is the motivation for bringing woolly mammoths back. But I think, you have to justify your funding somehow.
Yeah. Well,
so it's like, we're going to reduce global warming, but how cool would it be to have a woolly mammoth?
Are they the ones that started with the woolly mice, though?
Yes.
So they got a while to go, I think, before they reach mammoth.
And it's not too hard to increase to introduce these pores either. For example, like PVDF, if you dissolve this in acetone in a small quantity of water, the diverse evaporation rates of these, because the water in the acetone will dissolve at a different rate, will give you a very kind of mixed multimodal pore structure that ends up just being really effective at scattering.
Now, you mentioned some various additives earlier, so what are we looking at?
Yeah, you'll end up with UV stabilizers, which can help reduce yellowing and other sorts of absorption effects of UV, depending on what kind of pigment you're using. There can be more advanced dispersants, these like really charged particles that help prevent agglomeration and flocculation. Some rheology modifiers, thickeners effectively to control the viscosity, flow behavior, leveling, and film formation. And even some color additives, because not everyone wants their paint to be white.
Yeah, that was my first thought, is as cool as this is, if you're going to have white houses everywhere, it's not really effective.
Yeah, I think one of the primary applications of interest are the tops of buildings.
Mm-hmm.
I don't know if you've ever, like the top of Walmart, for instance, is just, no one's ever going to see that, and it's just reflecting directly up. But there's people who want to paint their homes, but of course they don't want something bright white, and they'd like a little bit of color in their life. And so you can get various additives that absorb within specific visible range. So you're going to be hurting your total reflectance a little bit, but maybe you're willing to give that up.
I did see a really good use case actually for putting it on top of data centers, since those already consume so much AC to keep it cool, that making it as cool as you can through other means is helpful.
Yeah, and they usually put them out in the middle of the desert where land is cheap anyways, and energy is cheap, so that makes a lot of sense. Now, so far we've mostly just been talking about paints. It's worth mentioning that there are a number of really advanced passive radiative cooling materials, and we'll touch on these briefly, but they're probably best saved for an entirely different episode because they're different and they're a little bit more complicated in the mechanism they use. But I wanted to highlight a few really interesting cases I saw. One included phase change materials into the radiative paints to add latent heat storage capacity. So during temperature increases, the phase change material is going to absorb heat by melting, causing that phase change, but it's not going to have a significant temperature increase during that period. So it can keep the temperature's situation kind of level. And then as things cool, it can then release this heat as it resolidifies. So it can heat during cooler periods and cool during hot periods. This generally enhances the overall cooling performance and provides a nice buffering effect, especially during particularly like transient heat loads. You could imagine a situation where you have some clouds where the sun kind of just beams out a little bit. So you're going to get beamed and then it's going to go away. Some other really interesting ones have photonic crystals. These are materials with periodic modulation of the dielectric constant at the scale of the wavelength of light. This creates ranges and frequencies where light propagation is forbidden, allowing for the design of materials with reflection or emission covering the full spectrum. So you can specifically tailor these to emit within that atmospheric window, making them a lot more effective potentially.
These photonic crystals, when I saw them, to me, they sound like something out of like Star Trek or like a sci-fi film. And kind of the same way with the next one, metamaterials. It sounds like something they'd use in a movie to make some sort of special armor.
Yeah, it definitely doesn't. Kudos to the person who got to name this thing. It's definitely a modern construction. These are artificially structured materials with sub-wavelength unit cells. Again, designed to achieve very specific electromagnetic responses. So these can be engineered with near perfect solar reflection and strong selective emission, just by tuning the geometry and the composition of the resonant elements. The big issue with these and the photonic crystals as well is that they need pretty precise alignment. So just spreading them all over the place kind of randomly with a paint, probably not going to achieve a particularly high effect. Not to mention that some of the gains here are potentially pretty marginal. Mm-hmm. But there's some interesting applications with solar cells or with thermoelectric devices where maximizing performance can have some real benefits.
The stuff that we've talked about so far this episode, it doesn't sound too difficult to just go into a lab and whip up. Even me as a mechanical engineer, I feel like I would probably be able to stumble my way through to at least making a marginal cooling paint.
Yeah, we'll put this in the show notes. There's a guy on YouTube who made some at his home, and he was able to achieve sub-ambient temperatures by like 6-ish degrees, just using barium sulfate, and not anything particularly complex.
So let's say that I decide to do this. How do I actually characterize the properties and actually figure out if I made a good paint or if it's kind of useless?
Yeah, we could do this in the lab or through field testing. In the lab, first you'd want to get some idea of solar reflectance. You can do that with a UV vis spectrophotometer. Equipped with an integrating sphere, and the integrating sphere just collects all of the reflected light over the solar spectrum. Then once you've collected this, you can weigh this by the standard irradiance spectrum. There's even an ASTM standard, if you're into that, G173, that you can use. That'll tell you exactly what to do. Now on the thermal emissivity front, we're emitting in the IR range, so we'll use a FTIR Fourier transform infrared spectrometer. Also, usually present in a lot of labs that are dealing with polymers or materials characterization in general. But the gold standard, right, you can do all the lab tests you want, is how it's going to perform out in the field. And this typically involves exposing the paint samples to outdoor conditions, so direct sunlight, some ambient air, the sky, and continuously monitoring their temperature along with the ambient temperature, solar radiance, humidity, wind speed. Often, interestingly, these samples are placed in insulated enclosures with a transparent IR window and some sort of like polyethylene film, because there's convective heat exchange between the surface and the wind. And so you're not actually isolating the effects of your cooling paint in response to sunlight. And you might actually not even be able to achieve subambient temperatures because heat is just being carried on the wind.
But you also may not want that, right? If you want to like actually look at the real world performance, it may be better to kind of throw it into the deep end and make it as real as possible, including uncertainty, sadly.
Yeah, it's usually common to report both values. And there's been a enough proposals to suggest a bi-layer situation where you have your paint, and then just like in normal paint, how you do a couple of coats, you might put a second coat that is going to be that insulating layer potentially.
That makes sense, yeah.
Sometimes measurements are combined into a solar reflectance index, or SRI, and this is a composite metric that combines the reflectance and the emittance into a single value, which just makes things easier. Although I'm always a fan of avoiding these joint values. It makes things easy to talk about, but you miss out on some critical nuance because there's situations where two very different measurements can achieve the same singular value.
As good as these paints sound, as with all things in life, there are some drawbacks. Specifically with this, there are some concerns over health hazards and potential negative effects it could have on you.
That's right. A lot of paints, there's issues with volatile organic compounds, VOCs, which are air pollutants. They're health hazards. They come from the solvent evaporating. And so there is a strong push towards low VOC or maybe zero VOC cooling paints. I think there's a company in the UK called Perta, and they have a water-based formulation that's very attractive to people who want to avoid those. Right now, the overall environmental footprint of these paints needs to be assessed all the way from mining to what you do with them at the end of their life cycle. I have to imagine that's going to be fairly similar to a lot of other paints, and potentially for these water-based ones a little bit better, often because, the alumina supply chain or potentially the silica or barium sulfate is probably nice and well established at this point. But there remains to be any sort of holistic study that covers this. Additionally, as we try to push for higher performing paints, this might include nanoparticles or microparticles, which raise concerns about their potential release to the environment and what you do at the end of their life. In fact, a lot of homes in Salt Lake City have used a lead-based paint, these brick homes, and now the brick is crumbling. And what are you supposed to do? That means the paint is also crumbling, and it's potentially leaching lead into the environment. And the challenge there is that to try to remove that, you have to put like this massive tent over the house and do all this really expensive scraping work, or just paint over it and delay the problem until later on.
Yeah, it's essentially a ticking time bomb at that point.
Yeah, and so whether or not the marginal gains of including certain things in there versus the possible long-term effects is something that is still needs to be assessed.
And a great way to find out more about ceramic particles is to visit our sponsor for today's episode, the American Ceramic Society Bulletin.
That's right. You could save hours of research time with the Bulletin archive. Instead of trying to get ChatGPT to make things up for you, you could go and use the Bulletin's expert-curated content that distills complex scientific developments into clear, concise intelligence so that you can focus on pushing the boundaries of material science with decades of research at your fingertips.
And this episode talked a lot about sustainability and helping out the environment, and how perfect is it that the May 2025 issue is all about sustainability and functionality in another industry that's really important, the glass industry.
That sounds really cool, and we could learn all about it if we go to ceramics.org/materialism to unlock full access to the Bulletin with a free ACERS membership.
The Materialism podcast is also sponsored by Materials Today. Visit materialstoday.com to stay up to date on the latest happenings in the material science field and read some of the fantastic articles that they have published. We actually used a few articles for today's episode.
Yeah, we'll throw them in the show notes and you can learn even more.
You can also head over to elsevier.com to find out more about their journals, books, conferences, and related programs.
As always, thank you for listening to this episode of the Materialism Podcast. If you have questions or feedback, please send us emails at materialism.podcast@gmail.com. Make sure you subscribe to the show on iTunes, Spotify, YouTube, or wherever you find your podcasts. And if you like the show and you want to help us reach more people, consider leaving a review, telling us what you think, how we can improve, and what material you'd like to hear about next. Finally, you can check out our Instagram page at materialism.podcast and see lots of cool art, connect with us, message us, and help us shape the future of the Materialism Podcast.
We'd like to give a shout out to Alphabot and Kolobyte for making the music for this podcast. They make a ton of cool synthwave stuff. You can find them on Spotify and YouTube. Thanks for listening.
Catch you next time.
The inventors of fire, electricity, magnetism, iron, lead, glass, silk, cotton, the makers of tools, the captors of lightning, the architect, the engineer, the musician, are all beneficiaries of the materials of this world and are bound only by their imaginations in manipulating those materials.